probably one of the most challenging things for setting up the iterated integral for triple integrals and even double integrals is finding the limits of integration. So we're going to do some examples to try to give us some intuition about how to find these limits and just be able to really do some practice in doing so. And so this first piece is we have this function, z equals 1 minus y squared. So that, if notice this is just a function of two variables. So z equals 1 minus y squared. Well, y squared is that parabola. Minus y squared is a parabola that goes down. 1 minus y squared is a parabola that goes down and is shifted up 1. So you have a parabola shifted up by 1 going down. But since you don't have an x value, it forms that cylinder, remember? It basically is just whatever is in the zy axis, and then it's just stretched along. So it creates that long cylinder. And you have x plus y equals 1 and x plus y equals 3. So these are the two, these are supposed to be parallel lines, by the way, they sure aren't. But what you also have this first octant. So what does that mean? The first octant means it's the positive case. So think of like the first quadrant where x and y are both positive. The first octant, x, y, and z are all positive. So it's that, that front-facing piece of that three-dimensional coordinate system. So that means the z values are all here, the y values are all here, and the x values are all that way. So this thing kind of runs up and butts up against this and stops. And it also stops flat at the bottom, and it doesn't go any more deeply into the board. And then these lines cut here, so they not only cut across, since they're lines like that, they actually slide up, they're planes. But I was worried about drawing that in a way that wasn't going to look horrible. I'm going to do that now a little bit to try to demonstrate. If you can think of those sort of like slicing, to me this kind of looks like a bread loaf, and you're slicing the bread loaf. I know it's kind of a dumb way to do that, but that's kind of how I envision that, as you're slicing the bread loaf. And so this purple region is kind of the region that we're considering in the xy plane. And the reason I say that's because in the z plane, the answer is pretty obvious for the limits. Z is bounded above by 1 minus y squared. So that tells me z goes from 0 up to this function. It's not overly complicated for z. Okay. Now for x and y. Now this is a little trickier, but what I notice is that in the y case, it looks like since we start in this and move out to that function, y goes from 0 to 1. Y is always sliding from 0 to 1. Y is sliding from 0 to 1. So that was dz and dy. I'm sorry. I want to do dy in the end because since these are constant bounds, it doesn't make sense to put them here. This leaves us the ability to define things in terms of y. So in x's case, I've got these two functions. So this looks like it starts here and moves towards that. So x is 1 minus y, x is 3 minus y. So 1 minus y to 3 minus y. And that's how you set that up. Now we could solve that. It really wouldn't be that bad to solve that. You just plug that in, that integrates pretty easily. You plug those in and you end up with some polynomials. This one wouldn't be too bad to figure out. But we're not here to do that. We're here only to find the limits. But over here, we have this region bounded below by this paraboloid. So this is the elliptical paraboloid, and this really is kind of a circular paraboloid. What you find is that what you're going to have is these concentric circles that go up. So When z is 0, it's just 0, but as the z value increases, it goes up. I'm going to try to draw, I've tried to draw this before, it's bad. I'm going to try. If it comes out bad, I'm really sorry. Like, I really wanted you to see this, but I'm just scared, right? So you have right, so you kind of have that parabola. It's not the worst I've ever drawn. And then it's bounded above by this sphere. This sphere has the square root of 6 as the radius. So you have some sort of radius. Appear to be, yeah, here we are. And so if I have some sort of sphere, whoa, that was terrible. So what you're going to have is something like that, where it opens up and then on the top is some sort of sphere. So it kind of opens up and there's some little rounded top where these things intersect. And the reason we want to do that is because the intersection point will tell us about where the x and y values are. So we need to figure out, where in the world do these two things intersect? And so to do that, we have to say, all right, well, when are these two functions equal to each other? I know that z is equal to x squared plus y squared. So I can plug that in here and say z plus z squared equals 6. Or I can rewrite that as z squared plus z minus 6 equals 0. Z plus 3, z minus 2 is equal to 0. So the two places where these things could possibly overlap is 2 and negative 3. But negative 3 doesn't make sense, right? Because we're always above the x-axis. So, above the xy plane. So that tells me that they intersect at z equals 2. That tells me about where they intersect. That doesn't tell me my z bounds, by the way. You might think it tells you your z bounds, but what that really is telling me, since z equals 2, that tells me about that. That tells me that the circle here is x squared plus y squared equals 2. So that tells me about how far x and y can go. So based upon that, let's think about just the circle. Let's not think about z squared yet. Let's think about just the circle. If I'm dealing with just this circle, I can say that x can get no smaller than negative square root of 2 and no larger than positive square root of 2. Right? Because if this was negative square root of 3, I would have 3 plus something positive or something that's non-negative is equal to 2, and that's impossible. So we have this piece. Then if we solve it, y is this plus or minus the square root of, so I have the negative square root of 2 minus x squared and the positive square root of 2 minus x squared here. And then I have to think about what z is. But in this case, it's actually easy, because they've told us that z is bounded below by this and above by that, which tells me that I'm going to go from x squared plus y squared all the way up to 6. The square root of 6 minus x squared minus y squared. So that's dz, dy, dx. And again, we could solve this, but solving this would be, you could do it. It would take you a while. You'd have to use trigonometric substitution. Notice we have to use trig sub. I'm not gonna lie. It ends up coming up a lot in these types of integrals. No wonder we studied it so much before. But the idea is being able to, the key takeaways here is A, drawing the problem and identifying each limit piece. Over here, drawing the problem helped, but recognizing that two equations are equal by doing some sort of substitution and solving was helpful in figuring out where those limits were and how we could construct the integrals from those limits.